The second main idea of Chapter 2 in our textbook is the idea of continuity. In simple terms, continuity just means connected. When you hear the word continuous, I want you to always associate that with the word connected. Because basically to be continuous means that you're able to trace the graph without lifting your pencil off the page. That would mean that there's no holes, there are no jumps in the graph because you're able to trace it without lifting your pencil, and there are no asymptotes. In other words, it's connected. So I always want you to associate the word connected with the word continuous. Now, being technical, we need to know how you are to verify or state using calculus whether or not something's continuous. So we'll begin by looking at the definition of continuity at an interior point. So we say that f of x is continuous at x equals c if and only if, and by the way, this if and only if means that it works both ways. This statement implies the second, and the second implies the first. So f of x is continuous at x equals c if and only if the limit as x approaches c of f of x is equal to f of c. What that is basically saying, so this is the calculus way of saying something's continuous at a point. What you need to understand is that what it's saying on the left, it's saying the limit of f of x as x approaches c. So we know that that means that is equal to the value of f at c. So this is the calculus view on the left. So they're saying the calculus view and the algebra view are the same. The limit as x approaches c is equal to the value of f at c. When that happens, the function's continuous at that point. So what that might look like is something like this. So let's say we have this function, and I will just take it on an interval from a to b. So let's say that's my function f of x. And then I find some interior point c. So to be continuous at c, which I have made this continuous at c, there's no holes or jumps, and I can trace this without ever lifting my pencil off the paper, is that the limit as x approaches c exists. And we can see that the left-hand side and the right-hand side are both approaching a certain y value. And since it's filled in right there, they're approaching the exact y value of f of c, the value of f that you would get if you plugged c into the equation. So another way to think about this is that the y values are coming together to the same value. The y values are approaching the same value, and the value they're approaching is also filled in. So it's continuous. There's no hole there. Okay, the limit on both sides exists, and not only that, but it's filled in right there, and it is equal to the value of f at c. So that's what it means to be continuous at a point technically. And remember, simply it just means that the function's connected everywhere. And then to also take care of all the details, we have another definition which is the same essentially, but just taking into account if we're dealing with an endpoint instead of an interior point. So we'll go ahead and use this interval a to b. So we say that f is continuous at the left endpoint, x equals a, if and only if the limit as x approaches a from the right, because a left endpoint doesn't have anything to the left of it, and so it's only going to have a one-sided limit on the right, which is okay if it's an endpoint. So this sort of takes care of that little detail. The limit as x approaches a from the right of f of x is equal to f of a. And then similarly, we say that f is continuous at the right endpoint, x equals b, if and only if the limit as x is approaching b from the left, because a right endpoint is not going to have anything to the right of it. It's only going to have stuff approaching from the left, which is okay if it's an endpoint. So the limit as x approaches b from the left of f of x exists and equals f of b, then f is considered continuous at that right endpoint. And then continuous on an interval is just basically saying that a function is continuous on an interval and let's just say a to b if and only if it is continuous at every point on that interval. So instead of looking at just one point, you look over an interval. If it's continuous, if this is true for every point on that interval, then it's considered continuous on that interval. Okay, so we know what makes something continuous. Now we have to look at the 4 things that would cause a function to not be continuous. We need to look at the 4 types of discontinuity. So I want you to keep in mind there are 4 of them. The first one is the least threatening, and that's the one that is referred to as removable. And you will see later how we remove them. The other word we use for the removable discontinuities is the word whole. And an example of what that would look like would be a nice, smooth, and connected graph everywhere else except right at that one point you would have a hole. Or sometimes you have this scenario where it's smooth and connected everywhere, you have a hole, and then you have some other value either above or below that hole. Those are the 2 types of ways you might see a removable discontinuity. Technically, what is happening is that this is when the limit as x approaches c of f of x exists. Okay, the 2-sided limit exists. The left-hand side and the right-hand side are approaching the same value. It's just that they don't equal the value of f at that point. Limit as x approaches c exists, but is not equal to f of c. So both sides are coming together toward the same point, but that point is not filled in. Or, if it is filled in, it's filled in somewhere else. So that's when you have a removable discontinuity or a whole discontinuity. Now, I want you to keep a little list or keep track of the types of functions that create holes. So we want to look at our culprits. There's 2 main types of functions that create holes, and the first main type of function is a rational function. Because sometimes you have zeros in the denominator, and those zeros in the denominator sometimes turn out to be holes. So zeros in the denominator of a rational function is the first culprit. The second culprit would be a piecewise function. So I'm going to try and squeeze that in here. Culprit number 2 would be a piecewise function. Because we're piecing different functions together, sometimes we have these holes filled in somewhere else, or sometimes they're just left open. So if you see a rational function or a piecewise function, be on the lookout for a hole. Second type of discontinuity is a jump. This is when you have different right and left-hand limits, because you might have this happening somewhere and then this happening somewhere else. And if you go to find the limit at that point, you can't, because the left hand and the right hand are not equal. They're totally far apart from each other. So we say that a jump discontinuity is when the limit as x approaches c from the right is not equal to the limit as x approaches c from the left. But it's important to note here that both limits exist and are equal to a finite number. So neither one of the limits are going to infinity. Both of the limits exist and both of them equal finite numbers. They just don't equal each other, and so we have a jump. Okay, the biggest culprit of jumps is the greatest integer function, is the biggest one because it has many jumps. And that's the one that looks like this, y equals intx. That's a huge culprit, so when you see intx, you know you're going to be dealing with some jumps. The second largest culprit is our piecewise functions. And this is an example. Here's a linear function pieced together with what looks like maybe a parabola or exponential. And when you piece these different functions together, sometimes they don't always connect. So piecewise functions is a big culprit of jumps. And then there's actually a third one. Let's move over here. The third culprit is this function that we looked at last week and other variations of that function where you have one of the values is 1 and then the other value is -1. So when x was positive, that equaled 1, and then when x was negative, that equaled -1, creating a jump right when you had 0 over 0. So this is another big culprit of jump, so keep your eye out for that function. The third type of discontinuity are asymptotes. These discontinuities are referred to as infinite discontinuities. But basically what they are vertical asymptotes. So that's when you have something that looks like this, where your y values might either be going off to positive infinity or they might be going down to negative infinity. So this happens when the limit as x approaches c does not exist. Because either the right-hand limit is approaching either positive or negative infinity, or the left-hand limit is approaching positive or negative infinity, or both. You could have one going off to positive infinity like this, one going down to negative infinity like that. You could have them both going off to positive infinity or both going down to negative infinity. At any rate, if you have either the right or left side going off to either one of the infinities, then that's a vertical asymptote. So the one and only culprit for these functions are rational, or sorry, for these discontinuities, are rational functions. Because more often than not, a 0 in the denominator creates an asymptote. Sometimes it's a whole, but more often than not, it's an asymptote. So whenever you have those zeros in the denominator, we're looking at an infinite discontinuity because it's a vertical asymptote. The last type of discontinuity is called an oscillating discontinuity. And this one we won't encounter too often. Every now and then we'll encounter it, but not too often. But that's when you have a function that starts oscillating so fast that it's hard to pinpoint the limit. So this is when the limit as x approaches c of f of x does not exist, Not because it's infinity, not because the left hand does not equal the right hand, it's just because it cannot be determined due to too much oscillation. So every now and then that'll happen, and then the biggest culprits of this, or the ones that mostly are affected by this, would be types of trig functions. These are the kinds of functions that are periodic and that oscillate. So now you know your 4 types of discontinuity. Now we'll continue with example 1. So in example 1, our job is to find the points of discontinuity. So we want to see what kinds of equations we have. And I notice here with A, I have a rational function. And I know that rational functions are the culprits of wholes and asymptotes. And wholes and or asymptotes are created by zeros in the denominator. So that's what I'm going to be looking for. So I'm going to take that denominator and I'm going to set that equal to 0. And I notice also that the denominator factors. It factors into x minus 3 and x minus 1. And so I'm going to set that equal to 0. And I notice that if x were to equal 3, I would have 0 times this number, which would be 0. I also notice that if x were to equal 1, I'd have, this would become 0 times whatever that number is, would still be 0. So I'm going to have a 0 in the denominator. When x equals 1 and also when x equals 3. Also, I notice that neither one of these factors gets canceled out. If it were to get canceled out, then it would just merely be a whole. But neither one of them cancel, so I have 2 points of discontinuity. I have an infinite discontinuity or an asymptote at both of those values. And so those are my 2 answers for part A. For part B, I have this type of function where I know that if I were to sketch the graph of this, I would have part of the function up at 1 and the other part of the function down at -1, because basically if x is a positive number, like 2, then y equals 1 because I have 2 divided by 2, or 3 divided by 3. But if x were to be a negative number, then I would have -2 divided by +2, which would give me -1, and so on. So I have a jump basically right when the value of x changes from positive to negative. So we would say that we have a jump discontinuity at x equals 0. So keep your eye out for functions that are like that one. Okay, in part C, I have a piecewise. So I know that the biggest culprit, or piecewise are the biggest culprits for, I'm going to look for either wholes or jumps. Wholes or jumps, because I'm piecing these 2 functions together. Well, I notice right away, actually, I'm going to have a whole at 0, because if you notice, 0 is simply not included in the domain. Okay, actually, let me clarify. It may not be a whole. I have to check. I know I either have whole or a jump at x equals 0. I know that I'm going to have an issue right there. What I'm going to do right now is check to see if the limit as x approaches 0 from the right is equal to the limit as x approaches 0 from the left. Let's check that out. So limit as x approaches 0 from the right, that would be related to this function here. So I'll find that limit by substituting, is -1. Then I'll go ahead and find the limit as x approaches 0 from the left. That would be using this function. And I'll go ahead and find that by substituting. So if you recall, e to the 0 is equal to 1, and then there's a negative in front, so that's -1. Okay, so what I notice is that the left-hand or the right-hand limit and the left-hand limit are equal, but the value of f is not defined at 0. So looking back at your types of discontinuity, that means it's going to be a hole, not a jump. Hole at x equals 0. If these were to be two different values, then I would know that it's a jump. But these values are the same. They're just not equal to f at 0 because f is not defined at 0. So that leaves us a hole right there. Okay, with example 2, we're given another piecewise. And we're asked to answer these questions, and this graph goes along with this definition here. So first it wants to know, does f of 1 exist? Well, there's two ways you could answer that question. You could either notice it right here, because I see that 1 is in the domain and f of 1 is 1, or I notice it right here. I have a point 1, 1. So yes, f of 1 exists and is equal to 1. Now it wants to know, does the limit as x approach 1, and notice there's no plus or minus, so that implies two sides. So it wants to know, does that two-sided limit exist? And so I can either look at the graph here, or I can look at the left and right of 1 and plug in 1. So I notice if I plug 1 in here, I'd get 2. If I plugged 1 in there, I'd have negative 2 plus 4, which is 2. So I can see that they're both approaching 2. Also, I can look on the graph. As I'm approaching 1 from the left and approaching 1 from the right, the y values are going up to 2. And they're both going up to 2. So yes, that does exist, and that equals 2. Then it wants to know, does the limit as x approaches 1 of f of x equal f of 1? Well, no, that is not true. F of 1 was 1, but the limit as x approaches 1 of f of x was 2. So is f continuous at x equals 1? No, it's not. We have what's called a hole, or a removable discontinuity. This is the least serious kind, but it is still a discontinuity nonetheless. This was open right here. So the y values were approaching 2, but f was not equal to 2 at 1. It was equal to something else. In example 3, they want us to sketch the graph and then locate any removable discontinuities. So I will begin by sketching this line. So for values of x that are less than 2, I'm graphing the line 3 minus x, which means it would have a y-intercept of 3, and then a slope of negative 1 up until 2. This is going to be open because I'm not including 2 in that portion of the piecewise function. I know that f of 2 is going to equal 2, so I know it's going to be filled in right there. When x is 2, f of x is 2. And then this would be also a straight line with a y-intercept of 0 and a slope of 1/2. So if I started here, I'd go up 1 over 2, up 1 over 2, up 1 over 2. And so there's the graph of my piecewise. So it wants to know if any of the discontinuities are removable, and the answer is yes, there are. There is one discontinuity, and it is removable because the left-hand limit approaching 2 and the right-hand limit approaching 2 are equal. They both want to go to 1. But they're not equal to f of 2. F of 2 is equal to 2. So there is a removable discontinuity. At x equals 2 because the limit as x approaches 2 of f of x exists but is not equal to f of 2. So that's what makes it a removable discontinuity. The two-sided limit exists. Both sides are approaching the same value of 1. It just does not equal the value of f at 2. Moving on to properties of continuous functions. These properties are going to show you some of the reasons why we love continuous functions so much and why we're always looking for the continuous parts of a function, because they're the easiest to work with. And you'll see why with all these properties. So if f of x and g of x are both continuous at a point x equals c, then the following is true. Then their sum would be continuous at x equals c. So this is for continuous. Their difference would be continuous at x equals c. So that could either be f minus g or g minus f. Their product is continuous at x equals c. Their quotient is continuous at x equals c. But hopefully you guys are recognizing as long as g of c does not equal 0. We always have to make sure our denominator is not equal to 0. But as long as it isn't, then f of g, or f divided by g, would be continuous at x equals c. And then if I were to multiply any of these functions by a constant, so if I had k times f or k times g, then either one of those would also be continuous at x equals c. And k here again is just referring to some sort of number, any real number. So for example, let's just say that f of x is equal to x squared and that g of x is equal to sine of x. Now clearly x squared is continuous for all real numbers because it looks like a parabola. So I can trace that without lifting my pencil off the page. Sine of x is very continuous. In fact, it just sort of oscillates up and down forever. And I never once have to lift my pencil off the page. So both of those are continuous functions. That means that I could add them. X squared plus sine x would be continuous. I could multiply them. X squared times sine x would be continuous. I could subtract them. X squared minus sine x would be continuous. I could multiply one of them by a number like 5 sine x would be continuous. I'll just put C is for continuous. And I could divide them and have a continuous function as long as, in this scenario, as long as x squared is not 0. Or as long as x is not 0, then sine x over x squared would be continuous. So that's just kind of an example of what we're talking about. So you can take two really simple functions and piece together more difficult functions that are still continuous and still very easy to work with. And then we can also take the composition of continuous functions as long as we're just careful about the domain. So supposing that f is continuous at x equals c, and g is continuous at f of c. So f is continuous at x equals c, and g is continuous at f of c, then g composed of f is continuous at x equals c. So what that means, so in other words, what that means is that the limit as x approaches c of g of f of x is equal to g of f of c. But in order for that to happen, f has to be continuous at c, because I'm going to be plugging in c, and then g has to be continuous at f of c, because f of c is what you end up plugging into the g function. Okay, so taking our original functions up here, let's say x squared is f of x, and then g of x is sine x. Well, then that also implies that sine of x squared is continuous. So I can even plug one continuous function into another continuous function and get yet a third continuous function. And since both x squared and sine of x are continuous at all real numbers, then this would be continuous for all real numbers as well. And I could also do the reverse too. I could have sine squared. So I could say that sine of x quantity squared is also continuous. because I can compose continuous functions together to get a third continuous function. It's very important that you know that. It might not seem so now, but it will become important later. It's also important that you know that the g of x function has to be continuous at f of c. Our last two examples, one of them is removing a discontinuity, and then the other one is sketching a graph. This here wants me to rewrite the function. It wants me to give a formula for an extended function that would make this continuous at x equals 1. So let's take a look and see what we're dealing with here. I have a difference of cubes in the numerator and a difference of squares in the denominator. I'm going to go ahead and just factor this out just to see if anything can cancel. And I notice right away that the x minus 1 terms cancel out. But what we need to understand is that if I were to plug 1 in here, which is, I'm trying to make it continuous at 1, if I were to plug 1 in here, I'd be dividing 0 over 0, which I'm not allowed to do at 1. I'm allowed to do it around 1, but I'm not allowed to do it at 1. So I'm just going to kind of leave this here, but I'm going to notice that the 1 technically is removable. The discontinuity at x equals 1 technically is removable because these factors cancel out. So let's see what's happening with the graph, and then I'll show you how to write the extended function. So what's happening with the graph is I have x to the third minus 1 divided by x squared minus 1. And I notice I only have one infinite discontinuity. I only have one vertical asymptote, and that's happening at negative 1. At positive 1, which is where the other 0 in my denominator was, it doesn't look like there's a big deal there. So let's go ahead and just check out the table of values really quick. Let me fix my table. I noticed that there is an error at x equals 1. It's just not showing up on my graph because what you can't see, and I can maybe try and zoom in. I don't know if it's going to help, but what you can't see is that there's a hole right there. It's still not showing. Let's try a little further. It's not showing us. The calculator has a hard time showing us holes, but technically there's a hole at x equals 1, which is not as serious as an asymptote. As you can see, the asymptote is much more serious. I have to really lift my pencil off that paper to graph that, okay? So the asymptote is not removable, but the hole is, and I'm going to show you how. So assuming I did cancel that out, this would be my extended f of x. I would just be left with this. So now I want you to take the calculator back out, and let's sketch the graph of this and compare. And let's compare these two graphs. There's the first and the second. They're pretty much identical. The only difference is where one had a hole or an error message, the other one filled in with the value. Other than that, their y values are identical. They are the exact same function. It's just the second one that I did, the extended one, has a filled in value, no longer a hole. So then the question is, where did they get that filled in value? They got that filled in value by plugging 1 into this equation. So if I were to evaluate this at 1, I'd have 1 squared plus 1 all over 1 plus 1, so I'd have 3 over 2. So this is one way to find an extended function for this one here. Option 2, and I'm just showing you this because this is the way the textbook did it, is they used a piecewise function. They said, okay, for all the values except 1, we're going to let f of x equal that. And actually, I need to exclude negative 1 as well because there's a vertical asymptote there. Oh wait, sorry, not equal to 1, and x not equal to negative 1. So f of x is equal to this when x is not 1 and not negative 1. And then we'll just go ahead and let f of x equal 3/2 when x is 1. And what that does is it basically just fills in the hole. So the nice thing about removable discontinuities, and that's how they got their name, is that they can be removed. We can fill them in. We can rewrite the function in a way that would fill in that hole, fill in that gap, and take out that discontinuity. The last example is, given some description of a generic function, sketch a possible graph. So answers always vary for these. Okay, I'm told that the right-hand limit as x approaches -2 equals f of -2, but the two-sided limit does not exist. So I'll go ahead and just make an x and y grid, and I'll locate my -2. And I know that the limit as x approaches -2 from the right, from this direction, has to equal f of x. So maybe I'll just have that look like this. So from the right, they're approaching some value, and that value is filled in because it's equal to f of -2. So every time you see that, think of that as filled in. There's no gap there, it's filled in. But the two-sided limit, it doesn't exist. So that means my other side must be somewhere else. So maybe it's like down here, and it's just somewhere else doing something else. So this is one possible graph for this description. And we're going to look at more of these in class. And if you have any questions, come see me in tutorial. I'll see you then. Bye-bye.